Hey guys, I am going to show you a little bit about relative frequency today. So let me flip my screen. Okay, relative frequency, let's talk about it. I'm going to make that screen a little bit larger for you. So, first we should talk about the opposite, theoretical probability. We've talked about that already. That is based on the total number of outcomes that are possible and the total number of successes that are theoretically possible. But what we're going to talk about today are things that actually happen. We want to talk about what we call experimental probability, or there's another phrase we can use to refer to it. It's just the title of this chapter. We could also call it relative, relative, there we go, frequency. So relative frequency is this. It is the quotient, which means we divide. And I'm writing on my phone, by the way, that's why I'm looking down. The quotient of the number of times a particular success took place divided by the total number of attempts. So this equation makes it look simple. You take the number of times you succeeded divided by the number of attempts made. Now look, this is what actually happened. This isn't like where we say, well, what if we rolled the dice? This is like, no, we're actually going to roll it and see what we get. Okay, experimental probability is where we actually went ahead and did it, and the total number of times we tried it was at the bottom. The total number of times we got what we wanted is on the top. So it says, like, if a basketball player made 7 out of 10 shots, they actually made those shots, we would say the probability is 7 out of 10, or 0.7. But if we were talking about, like, what would happen, how many times would I roll an even number on a die, that is what I would expect to happen. That's called theoretical probability. We're not talking about that. We're talking about relative frequency, which is also called experimental probability. So we're actually going to do something experimental right now. It says calculate the probability of rolling a die and getting it to land on a 3. Now let's pause right there. Theoretically, how often should we expect it to land on a 3? Well, there are 6 sides of a die. Of those 6 sides, only one side has a 3 on it. So we would expect it to be 0.16 repeating. That should be the probability of landing on a 3. Now, we're actually going to use a dice simulator. I'm not going to roll 5 dice in front of you and then hold them all up. I'm pulling up the simulator. So here's a dice simulator. I'm going to roll 5 virtual dice right now. So I'm rolling them, and dang it, you don't have a single one that's a 3. So for the 5 times, I'm going to write down that of the 5 that I attempted, how many successes did I have? That's what goes on the top. Well, 0. So 0 out of 5 would be a probability of 0, or 0%. Now we're going to try it 20 times. So let's actually go back, and let's roll this thing 20 times. Let's roll dice. So we had 1, 2, 3 times. So 3 times it landed on, let me full screen this again. So 3 out of 20 times I landed on a 3. That would be 15%, or 0.15. A probability of 0.15. Okay, not bad. Now let's try it 50 times. So let's come back, and we're seeing how many 3s we can roll if we rolled 50 dice. So here you can see we have 1, 2, scrolling, 3, 4, 5, 6, 7. Looks like 7. So 7 out of 50, which is equal to 0.14. Now, what did I say we're supposed to get closer to? We're supposed to get closer to 0.16. Now, some students might say, like, okay, first we were off, and then it's like, yeah, we got better, but we should expect this to be even closer. Well, that's not how it always works. And here's what this thing that we're talking about is actually called. Let me come up here to see it. It says, this is actually called the law of large numbers, and here's what it says. The more times we try something, the closer we get to the theoretical probability. Let me say that again. Oh, and I should make this bigger. The more times we try something, the closer we get to the theoretical probability. So yeah, I rolled it 50 times, and it's not that every single time, like if I roll one more die, I'm going to get a little bit closer. But how it means is, in general, the more times I try something, the closer I get to the theoretical. It's kind of like the idea I could flip 2 coins and they could both land on heads, and that doesn't prove wrong that it's a 50-50 shot. But if I keep flipping it over and over and over, thousands of times, like hundreds of thousands of times, millions of times, I would find that overall it's about 50% of the time heads, 50% of the time tails. The law of large numbers says if you have a large number of times you do it, it's probably like the theoretical probability will eventually kind of show itself. So let's answer some questions about all this stuff. So it says Wendell, whoops, let me zoom in a little. Wendell flips a regular coin 3 times and it lands on heads each time. His conclusion is that his coin always lands on heads, every single time. Prove a way to help Wendell to see he's wrong. Well, my recommendation would actually say, flip it again. And I'd say, and again, and again, and again, until you finally get tails. That could help convince him. Otherwise, I would say he can't be convinced. He needs to see that it could be tails, because the law of large numbers says if you keep doing it more and more and more, eventually you're going to see what the theoretical probability actually is. It's just like in a basketball game. A player might get really lucky and make 1 or 2 shots, but if you make them take foul shots over and over and over and over and over again, you'll eventually figure out if they're actually good or bad. You'll actually figure out their true probability of making a shot. Number 2, when playing a board game, Roger spent 3 turns rolling a 6-sided die, and it happened to roll on a 6. It took until his 3rd turn for him to roll a 6. Was this luck, or is 3 turns the amount of time we would expect it to roll a 6? Well, let's talk about the theoretical probability of rolling a 6. So theoretically, we would expect it, well, there's 6 options, and there's only one side that has a 6. So 0.16 is the probability that it would land on a 6. Now, 1 out of every 6 rolls, it should land on a 6. So if it's at most, or if we would expect it to take at most like 12 rolls or 20 rolls, all right, let me pause that. Let me go back to what I was saying. 6 is what we expect. Okay? It could happen in like 12 or 20 rolls. It might take a lot longer, or it might take a lot shorter. Just like in this case. This time it only took 3 turns for him to get a 6, but sometimes it might take a lot more turns than 6 rolls just to get a 6. But 6 rolls is what we expect. So 3 is better than expected. Okay, we expected it to take 1 out of every 6 rolls. So if it took 3 rolls, 3 is better than expected. So yeah, you could call this luck if you wanted. I don't believe in luck, but you could call it that. Okay, let's look at this. It says first calculate the probability of a spinner with 6 equal sections landing on any one given section. Then go to this link and fill in the frequency table. So I am actually going to pull that up right now. I think I remember the website, NCTM spinner. Good. It looks like I've been there already. Okay, so I have a 6 even spaced sides, and it says I'm supposed to do this 20 times first. So let's change this number of spins, 20. Let's spin it. Boom, green. Okay, so you can see, so we have lime 100% of the time so far. Oh, now 50% of the time it's been blue. We got a purple, so we've only had purple, lime, or blue. And you can see over here is the theoretical probability, but the experimental probability changes every time we spin it. It's landed on lime 2 out of 5 times. Oh, now it's landed on purple and lime 2 times. You can see experimental is constantly changing because the experimental is the number of things that are actually happening. Now, because of the law of large numbers, we would expect this to get closer and closer to 16.7. None of our numbers are really at 16.7. Let's click skip to the end. Okay, so we don't really have any numbers other than lime that's close to 16.7. But let's go back and answer the question. Okay. We're calculating the probability of a spinner with 6 equal sections landing on any one given section. Let's actually pick a color and focus on that color. So let's focus on which one's furthest off, purple. Or we could do yellow. Let's actually go with yellow. Poor little yellow. So yellow for right now had 5%, which was only 1 out of those 20 spins landed on yellow. So 0.05. So poor yellow. We're rooting for you. Now, what we expect it to be, based on our theoretical probability, they said is 0.16, is actually 0.16 repeating. So that's what we're expecting. 1 out of 6 is 0.16 repeating. Let's spin it 50 times and see what happens. Now, what I've said is the more times we spin it, the closer we expect it to get to this. So let's go and go 50 times. Let's hit spin. Oh wait, I actually want to reset this, I'm sorry. So, let's spin. Okay, so now it's looking like purple's going to roll the roost. And we're hoping for yellow. And you can see we could actually sit here and watch it go all the time. We're hoping this gets close to 16.6 repeating. But so far we haven't gotten any yellows. Let's skip to the end. Okay, so in the end we got 7 out of 50, it says. So 7 out of 50... I should zoom in a little. Oh, it's not really letting me. 7 out of 50 spins, which is 0.14 times, it got close to... not got close, it landed on yellow. You can see we're actually getting a little bit closer to that 0.16 repeating. Let's try spinning this thing 200 times now. So let's go in here, 200. Let's reset it, and let's click spin. And we want to see how many times it lands on yellow. Well, so far, no good. Nothing on yellow. Nothing on yellow. And so you might be giving up right now, and you might say, oh, good, yellow has a chance. But you might say, yellow is 33% now. Maybe yellow is going to say, oh, it's down to 25. Well, eventually, this is going to kind of level out, and we're expecting it to get close to 16.7. Let's skip to the end. Okay, and yellow now was 31 out of the 200 spins, which is 15.5%. So we just said that was 31 out of the 200 spins, which is 15 point, I'm going to put 0.155 probability. You might, again, notice now we're getting closer. Kind of like earlier, it's not that sorry. That was on the other page. It's not that every time we're getting closer, but we would expect it to get closer. Although we might have a fluke and maybe we'll get a ton of yellows this time. So now let's make it spin it 1,000 times. Let's reset. Again, we could watch it and we could say like, oh man, there's no hope. Landed on red, it's never going to land on yellow. But we have to have faith. If we spin it more and more and more, there we go, there's yellow. Eventually, we should find that they would all even out and be really close. Let's skip to the end. And look at yellow now. 170 out of 1,000, which I need to make this bigger. 170 out of 1,000, which is 0.17. Isn't that closer to 0.166 repeating? And it's kind of cool with this website, because we can go up and we can make it, let's make it 10,000. Spin, oh wait, I'm sorry. It actually, 1,000's a cap. I take it back. This website's cool. It could be cooler if you could make it 10,000. Let's get to the end. This time it was 17.8%. This time it was 16.7, which is almost exactly what we expected. This time 19.6. So you can see it's not always the same. 16.9. But if we kept spinning this over and over and over, thousands of thousands of thousands of times, we would expect it. Oh, here we go. See, I've done it 5,000, 6,000, 7,000. See how I'm not clicking reset now? I just spun it 10,000 times. Look how close it is to 16.7. And the more I spin, the closer it'll eventually get. And sometimes it'll be off. Like, see, it rose to 17.1. But and it's now rising to 17.2. But eventually you've got to have faith that eventually it's going to come down. It's kind of like your body's temperature. It might fluctuate a little, but eventually, like it's 17.2, 7.2, it'll eventually come down. I'm getting quicker at going back and forth here. And I just think this is interesting, because like, look, 17.1, 17.2. And it'll eventually settle down and get really close to 16.7. I don't really want to keep doing this. I just did 80,000 spins. And you can see they're all pretty close to 16.7. You can do this on your own. Let's get back to the lesson. So, anyways, moving on. Oh, next page. So we want to answer some questions. So Manuel bought a weighted coin that lands on heads 2/3 of the time. If he flips the coin 9 times... Wait, did I have any sort of lesson about this? Oh yeah, I'm sorry. Okay. Making predictions. I said, as you already know, it's much easier to make a prediction regarding how a coin will be flipped compared to if you go have a shot in basketball. Because there are so many factors that affect whether a basketball goes in a hoop. What we can do, though, is we can use past experimental data to predict what we think is going to happen. So basically what we're going to do is we're going to take our relative frequency, our experimental probability, and we multiply it by the number of times we're going to try something out. So now let's look at these questions. So A coin lands on heads 2/3 of the time. What's the if he flips it 9 times, how many times would it land on heads? Well, 2/3 of the time, it lands on heads. If we flip it 9 times, well, 2/3 times 9, I can make this 9/1. I can cross simplify there. 6 times, we would expect it to land on heads. What we do is we take our relative frequency and we multiply that by the total number of attempts, the number of times we're going to try something. So of 9 tries, 6 of those would be heads, 3 of those would be tails. So here, this spinner is spun 30 times. How many times would it expect it to land on the green section? Well, 2 out of the 8 sections are green. And we actually can simplify 2 out of 8. That's the same thing as 1/4. So 1/4 of the sections are green. If we spun it 30 times, well, 1/4 times 30 would tell us how many times we'd expect it to land on a green section. Again, I could cross simplify. 2 goes into 4 twice, 2 goes into 30 15 times. So we could write our answer as 15 over 2, or 7.5 times. Which we really can't spin a spinner a 0.5 of a time, so we would say about 8 times. We would round. So again, just take the relative frequency, divide by or multiply by the total. The next example, the third one. When running for office, Ravi surveys people at random to see who they'll vote for. And there's also shown here, if there's 320 people in his grade, how many votes can he expect not to receive? Okay, let's see how many votes he did not receive. So you can see there were 3 votes for Danielle, 5 for Tamara, so 8 votes he did not receive. Well, 8 out of how many? 8 out of 11 plus 3 plus 5 would be, why am I blanking here, 19? Yeah. That's just, I don't know why I chose that number for this problem, because it's not going to work out nicely. Maybe that's why. But anyways, I have 8 out of 19 that he did not receive. That is our experimental probability. That is our relative frequency. But we don't just have 19 people in the grade. There's 320 people in the grade. So we have to multiply by 320. So I'm going to use my calculator here. 8 divided by 19 times 320. I found the answer to be, I should put the squigglies. That's not the technical word, the approximate symbol. About 135 people. It's 134.7 something. So about 135 people, or how many votes, will not vote for Ravi. Ravi's expected to get then almost 200 votes. Way to go, Ravi. I should actually... Oh, good, I'm glad I checked the bottom. No, this question could have been solved with proportions. And that is true. Proportions can be used to solve these. Every probability is a fraction. I mean, if we wanted, we could have said 8 over 19 equals x over 320, right? And then just cross-multiplied and solved that. So that is an option. Okay, let's answer these, and then let's call it. Roberto just took 2 putts and completed 14 out of 50 holes of golf that he practiced yesterday. If he's going to have a full round of 18 holes, how many holes can he expect to 2-putt? So he did 14 out of 50. But now, so that's a relative frequency. Okay, that's like what he did actually. Remember, experimental probability is what actually happened. We can multiply that by how many times we're attempting something, in this case 18, to find our answer. So I'm actually just going to type that in. 14 out of 50 times 18, and I got an answer of 5.04, so about 5 holes. See, these aren't bad. You just take the relative frequency and multiply by the total. Gary randomly hits emojis on his phone to send to his mom. If he clicks 20 different times, how many frowning emojis can he send? Well, how many of these are frowning? The devil one almost threw me off. I thought it was frowning. It's just bad. Okay, so these 2 are frowning. So 2 out of 1, 2, 3, 4, 5, 6, 7. So 2 out of 7 are frowning. That's a relative frequency. Whoops. And we can multiply that by the total number of things, the total number of attempts, which is 20. So 2 divided by 7 times 20. I don't use a fraction button. I type in 2 divided by 7. I get about 5.71, which I would say about 6 emojis. So of those 20, about 6 of them are probably going to be frowning. That's what probability is. It's telling us what probably is going to happen, the likelihood of what could happen. So, a new medication for treating poison ivy, which I need, I get it bad, is being developed that is hopefully going to get rid of symptoms quickly. If around 50 million Americans, which apparently that's how many Americans get it per year, I did Google it, get poison ivy this year, how many would be healed by this medication? Okay, so you can see how many would be healed. Well, some are healed in a day, some are healed in a week. Let's actually add those two things up. So 97 plus 278. So 375 people are healed out of, I'm going to add 392 to that. If you add up all the numbers in this table, you get 767. So the two healed numbers out of 767 is how many we expect to be healed. Well, if we multiply that by 50 million Americans, we should find how many Americans we would expect to be healed. I mean, I'm just going based on this right here. Doesn't it look like that's almost, doesn't look like that's almost half. So I'm guessing around 25 million Americans. So let's take 375 divided by 767, which again, I think it's around 0.5. Yeah, it's 0.488. And I'm going to multiply that by 50, 1, 2, 3, 1, 2, 3, 50 million. And I get an answer of this. 24,445,893, and then it's like 0.09. So about 24,445,893 Americans are expected to be healed from this. Again, take the probability, multiply by the attempts. Last question. A six-sided number cube is rolled 80 times. What's the best probability or best prediction for the number of times it'll land on a number that's a factor of 12? Okay, let's list all factors of 12 that are on a number cube. 1 goes into 12, 2 goes into 12, 3 goes into 12, 4 goes into 12, and 6 goes into 12. So of all the sides on a die, 5 out of 6 of them go into 12. So if we multiply that by 80, we should know how many times it's going to land on a factor of 12. So 5 divided by 6 times 80, we get about, it's exactly 66.6 repeating. So I would say about 67 times it's going to happen. And if you can't hear, Barry is crying behind me, which means it's probably time for me to go. So hopefully this lesson helped. There's a bunch of questions to practice, but it is time for me to call it.